Morning, everyone. Thank you for coming to my PhD defense. The title of my PhD thesis is towards conflict-free switching in multi-hop wireless mesh networks. This work is done under the direction of Professor Dmrbi. Here is the outline of this talk. First, I will give a brief introduction to high-speed wireless mesh network and the problem approach for this kind of network. Then we will design the first protocol design is D-LSMA MAC, which establishes distributed link scheduling multiple access solutions. Then, based on the observations of D-LSMA design, I would like to discuss the relationship between interference modeling and the scheduling complexity. After that, I will present the second protocol design, which is named IRMA. It's a joint integrated routing and MAC scheduling solution. Finally, I will summarize the talk with some conclusion and the future work directions. In the recent years, with the development of broadband radio, the wireless mesh network emerging as a very powerful technology to replace wide infrastructures. This diagram shows our vision about the future high-speed wireless mesh network. In the center of this diagram, there's a group of mesh routers, which form a flat mesh structure connected by short-range high-speed broadband radios. And some of the edge routers can have additional interface to interface with other networks like cellular or internet, or connect to other clients like the home electronics or IP phones, TVs, and computers. So basically, we think this kind of architecture is a very promising solution for future in the small home and office environments, because it can use this broadband radio to establish a high-speed wireless data transport hold long in L to support the multi-hop wireless peer-to-peer transport. And because there's no wiring cost, it can be easy to deploy or dismantle. So this PhD research is mainly focused on the protocol design of the core mesh backbone, which is shown in the yellow cloud. We think this core network can be modeled as follows. First, network is of a mesh grid topology, and the size is probably less than 100 nodes, and the routers has very limited mobility, and the links which submitted to core channel interference. The traffic are modeled as a aggregated client traffic, which generated by end-to-end operations like internet browsing, voice, video, or bulk data transfer. The performance issues about protocol design are mainly focused on how to exploit these broadband radios to have high throughput and end-to-end throughput and low delay, and fairness issues and quality of service. So the problems we try to address in this thesis is as follows. First, what is the theoretical achievable end-to-end rate given a certain number of nodes and traffic in the topology like this? And what is the dynamic protocol designed to solve this MAC and routing for a dynamic system? Is there any heuristic design to approximate the optimal capacity? And if it has, what's the control overhead, and how does it scale with the network growth and traffic demands change? First, let's look at the current approach. The conventional approach for wireless mesh network is to use IEEE 811 as a PHY and use IEEE 811 MAC to solve the channel access problem, then combined with some common routing protocols such as ad hoc routing. The problem with this kind of approach is because due to it has a lack of coordination and control, the contention-based MAC protocol fails to handle interference and cause problems such as hidden terminal, exposed terminals. Also, the interaction between MAC and routing protocols are very poor. It will create self-interference problems and the interflow interference problems. So in all, the end-to-end performance for this kind of design, the throughput is much lower than the underlying link capacity, and the performance is unreliable and some unfairness issues. So to avoid these shortcomings, we abandon this bottom-up approach and try to have a top-down perspective to see what is a plausible architecture to ensure end-to-end performance. So we propose our wireless switching architecture. This kind of idea actually comes from some operations from telecommunication network. For example, in the telephone network, the circuit switch actually can arrange a limited number of circuits for a large number of core connections with some switching algorithm. Also, in the ATM network, ATM packet switch can establish virtual circuits to allow end-to-end fast switching for multiple flows at the same time. So by combining these two design philosophy, we try to propose the wireless switching infrastructure to establish conflict-free switched paths for end-to-end flows. Switching here has two meanings. First, it needs to solve inherent wireless transmission conflicts by some kind of time or frequency switching, which I show in this animation. So at each time, there's only a subset links are active. And because these active links are interference-free, there's no need for contention, back-off, collision, and it's very easy to, with these established link activations, to set up end-to-end connection pipes to provide controllable point-to-point bandwidth guarantee over the wireless mesh network. However, to realize this, it really needs some kind of disruptive design for protocol stack to establish some vertical control in the protocol stack. My current PhD research is mainly focused on a single-channel wireless mesh network, so there's no frequency selection in the picture. So we mainly talk about time switching. So for this, we introduced two main designs. Here is the protocol activity of these two designs. The D-LSMA, we try to use some method to regulate MAC scheduling. Basically, we introduce a scheduler between the MAC and the routing, and have the data and the control signaling mixed in one same channel. Also, we have some kind of interface to have extensible, to make this design extensible to support flow QoS. And different from this DMA design, we also propose joint routing and MAC scheduling design, which we try to optimize both TDMA MAC and the routing path selection with the IRMA agent. And this IRMA agent is actually working in a separate control plane, which is physically independent with the data plane, and can have some advanced QoS reservation and mission control mechanism implemented upon it. For this time switching case, you really need to understand that the different scheduling results actually have dramatically different performance in wireless channel access. Here we use example to show different link access scheduling solutions in anecdotal topology. Here we assume that the receiver only affected by interference from his one-hop transmitters. You can see that if there's no any coordination in the random scheduling, it's very easy to cause collisions, such as the hidden terminals here. And by removing these conflicting transmissions, we can have the conflict-free scheduling, like in the case in the second picture showing here. However, the long conflicting links shall not be unduly prohibited. The special use of the whole network does not reach its maximum point until there are no more transmission coexist. So from this picture, we can see if actually the transmission from C to D can also be scheduled at the same time. So we call this kind of scheme is the maximal scheduling. And on the other hand, to find the maximum number of coexisting transmissions in this picture is an NP-hard problem, which calls maximum scheduling. So basically, there are a lot of theoretical research about theoretical analysis about how to reach maximum scheduling and maximum scheduling. But in practical, many protocols in practical are only achieve this kind of performance. So our thesis in this thesis we try to develop protocols to bridge this gap, to have some advanced control to establish link transmission, link scheduling, to reach maximum scheduling or maximum scheduling.
So why would you actually want to have maximum scheduling? I mean, is that real perspective? I mean, a real-world application perspective.
Um,
I mean,
yeah, basically, the maximum scheduling problem is not very easy to solve in distributed protocol. It's if you have a centralized algorithm, you can solve it. Even if it's NP hard, you can solve it for a small size of network some way.
right.
Yeah, I just
You can
yeah.
achieve maximum throughput.
Yeah, but if one of those guys doesn't have anything to send, then why did you go solve that equation?
Oh no, this is
You're assuming here that everyone has something to send? I mean, take the...
So here in this picture, we assume everyone has something to send, but in the protocol design, we assume that this scheduling will be based on the link switch has traffic to send. So basically, you can say there's like a subset of a graph, which yeah.
So would this be something, though, where you would pretty much require a fixed topology in order to actually even care about this? Because, I mean...
Yeah, so basically we assume that this kind of topology is for the static mesh network. So basically the topology change is not very frequent, or is in a very low time scale.
I can see that from a wired point of view, but even a mesh network, can you really justify that it would be that static? I mean, the wireless channel itself might be variable enough.
You mean the physical layer characteristics?
Yeah.
Yeah, for this one, you can assume there is some kind of physical layer solutions to ensure some kind of link capacity, which is achievable link capacity. So basically, each link can be estimated as there's a certain bandwidth, which by consider all the kind of fadings or something like that. So the scheme can based on that assumption. Suppose actually in the real protocol design, you also have to might have some error control mechanism incorporated in here to compile the channel errors some way. Yeah.
So I'm not complaining. I'm just saying that you don't actually really need to worry about this case D, because I don't think case D is actually a realistic assumption for your problem. Whatever you're doing is more realistic.
Yeah, okay, I agree. So this is a table which compare our D-LSMA design, IRMA design with the traditional H11 scheme. So basically, they are targeted for different scenarios. For example, H11 is used mainly for the star topology wireless LAN or multi-hop wireless LAN, and D-LSMA can be used for multi-hop ad hoc network, and IRMA is mainly used for static mesh backbone, which has to support long-lived flows. The traffic pattern for the other scheme is any because they are only layer 2 solutions. IRMA is actually integrated layer 2 and layer 3 solution. So they are also based on different interference model and have different schedule unit. So basically, both D-LSMA and H11 is perfect scheduling solutions, and our IRMA is scheduling for end-to-end flows. The control mechanism is also different. D-LSMA is actually using the data control in the same channel, and IRMA has a separate global control plane. So we try to, through this design practice for D-LSMA and IRMA, we try to find the relationship between the interference model and the scheduling unit and the control mechanism, how it affects the total system performance.
So here you didn't compare with 802.16 based multi-hop network, huh?
You mean the WiMAX network? Yeah, I don't, because the baseline approach here I compiled is the H11 plus some ad hoc routing protocols. That's the baseline. Yeah.
That's more TDMA based.
Yeah, and I have not considered that because it might be interesting to compare my IRMA approach with that later in the future work. Yeah. So this is the literature review for protocol design for multi-hop wireless network protocols. Basically, we classify the MAC protocol design for multi-hop wireless network as following 4 categories. The random access and carousels-based multiple access are basically cannot solve hidden node problems. And some kind of fixed TDMA access actually is not suitable for dynamic system design. So most of the working protocols are of this category, say dynamic reservation. And dynamic reservation, we classify this in 2 categories. One is per packet scheduling, the other is the flow rate-based scheduling. There are many working protocols just propose to schedule single packet, which like some is using the TDMA slot architecture or some without TDMA slot structure. For end-to-end packet scheduling, there's one work proposed by Arupa and Sachin is the D-LSMA MAC protocol. And for flow rate scheduling, there are many algorithms and many theoretical work about how to have perfect edge coloring algorithms, but there's no real protocol design. Within the IRMA is to my best knowledge, is the first protocol proposed to have some kind of end-to-end flow scheduling established. Also, regarding the routing protocol design, there's some simple routing protocol use hop metric like DSDV or DVDSR proposed for ad hoc routing, which is targeted for providing mobility solutions. Also, there are some kind of cross-layer routing design like ETX, ETT, and PAMA, which try to incorporate some physical layer and MAC layer parameters into routing metric. Within this kind of parameter exchange between routing and MAC is not enough to address the fundamental inefficiency of MAC problems. So that's why we want to have a joint routing MAC and routing design, which like we are going to do in the IRMA protocol. So next, I will going to describe the D-LSMA design. First, I'm going to discuss some problems with the CSMA MAC in multi-hop wireless mesh networks. Then I will talk about the principle and protocol design for D-LSMA, and then I will give some simulation results and some discussion. Why H11 MAC is bad for multi-hop flows? First, because there's some significant overhead, because you have to contention have to be done for access channels for every packet access. Secondly, there's a paradox between hidden terminal problems and exposed terminals. When you use the RTS-CTS to solve the hidden terminal problems, you actually create the exposed terminal problems which waste the bandwidth usage. For example, here, when A transmitted to B, RTS of A and CTS of B actually prevent the D and F to access channel at the same time. So basically, nodes within RTS-CTS range lose chances of parallel transmission and reception. The other problem with H11 MAC for multi-hop flow is that there's a head-of-line blocking problem, because there's no differentiation among multiple link destinations. A node in a multi-hop network, for example, at A, he might be responsible to transmit multiple flows to different destinations. As these all packets are put in the same queue, if the head of the queue, for example, this packet to the yellow load is blocked, they don't have the chance to utilize the link access capability to reach other destinations. So opportunities is blocked by this head packet of queue. To really eliminate both hidden and exposed terminal problems, a new transmission configuration model is introduced here. We call it a one-hop interface model. Basically, we change the RTS-CTS scheduling rule to one-hop link scheduling rule. The RTS-CTS scheduling rule requires that all nodes that are within the one-hop communication range of either the transmitter or the receiver cannot transmit or receive. So here that all the links or nodes shown in the gray color are masked by the RTS-CTS handshake. The one-hop link scheduling rule is different. Basically, we require that the condition for parallel transmission is changed that 2 links can be scheduled at the same time when there's no direct cross-link between the transmitter and the receiver in those 2 pairs of TX-axis nodes. So basically, suppose we want to have a packet transmission from this node to this node. If this happens, not like the RTS-CTS in the physics model. There are some link capability. There are some link transmission opportunities which can be utilized parallelly to increase the spatial use of the whole network. So to enhance 811 MAC to have this kind of capability, we make two major changes in the D-LSMA MAC model. First, we address that head of line blocking problem. We classify packets based on different destination, and we introduce a scheduler which is presided between the MAC and the routing protocol to reserve a good transmission time for the packets based on these different destinations. And in the MAC state machine, we change the default 811 state machine, which basically only have 3 states: free, prohibited, or reserved, to a state machine which have 2 additional states, which included here is TXOK and IXOK. So in 811, when you overhear any RTS-CTS frame, the node immediately goes to prohibited state and cannot use cannot access the link. Here we introduce these two additional states, TXOK, IXOK, to allow parallel transmission and receptions, even when the nodes already heard RTS and CTS frames. This is actually implemented as following. So we need to separate the reservation with transmission. Basically, there is an artificial control gap is introduced between the RTS-CTS exchange and the ensuing data frames. Within this reservation gap, we can allow multiple RTS-CTS handshake happen to have parallel transmissions. And the node in TXOK or OK state can still reserve overlapping transmissions even when hear RTS and CTS frames. To allow this, we also change the format of RTS frame. For example, this is the original RTS frame, and we rephrase the NLV vector to only cover the RTS-CTS handshake, and introduce 2 additional parameters like T0 and TD, which shows the extended beginning time of the data frame and the length of the data frame. Also, to make this can be extended to flow reservation, we introduce 2 additional parameters. T is the periodical data arrival time, and the number of is the Rn is the number of reservations, which we want to reserve for this one RTS-CTS handshake. Basically, with this kind of mechanism, we can reserve multiple packets in one RTS-CTS handshake to reduce contention. And to allow this, we also disable SK equilibrium frames and magnetic transmission. So we think that this kind of scheme can be used to transport real-time flows, and the channel errors and the transmission failures can be handled by some end-to-end error control alternatives. And because this is a distributed scheme, the time synchronized can be solved as same as the 811 schemes.
What is the Rn here?
Rn is how many number of reservations you want to make in this one RTS frame.
Okay.
So basically, for here, the Rn is 3. You try to reserve the 3 data transmissions. Suppose there are 3 data packets in the queue. Yeah. So we use an example to show how D-LSMA algorithm works. Basically, this example has a 5 node in a mesh topology like here. And there are 2 single hop flows, A to B and D to C, want to be reserved. So we will use this example to show how nodes mark the schedule table based on labeling RTS-CTS and how to enable overlapping reservations. So this is the legend to show the different MAC states. At the very beginning, all schedule empty, and after the first RTS-CTS handshake, suppose the A, B successfully reserved the transmission for 3 data packets, showing it here. You can see that A and B marked their schedule as reserved, and E marked that as prohibited, and C actually, because it only here B CTS, it can mark it as IXOK. Then when D send RTS frame because she thinks this is his schedule for the proposed transmission is okay. She can allow the DC transmission overlap with the AB transmission like this way. So basically, here we establish a parallel transmission between two flows AB and DC, which is not able to do in the traditional 811 MAC.
So in your example, when C send the CTS back to D, is that possible to collide with B? Because B gonna receive data from.
No, though we have here we have a resolution gap between the RTS, CTS, and data frame.
So this only
Yeah.
happened within the reservation period. You see?
Uh,
Or this completely.
so I introduce an artificial resolution gap between the between the RTS, CTS reservation and the data frame beginning time. So basically, this will give some additional space to allow parallel transmissions.
So this happened for every RTS, CTS?
Yeah, yeah. This resolution gap is all you have to pay to have this kind of capability to allow parallel transmission.
How did you estimate this gap?
So this is a good question. Actually, currently we this gap actually is depending on how many parallel transmissions you try to arrange in the neighborhood. It depends on the density of network and traffic density, something like that. Currently, in my simulation, I use the fixed time length here, which is able to allow 3 RTS, CTS handshakes, something like that.
But the gap is not in your frame format.
The gap is not in the frame format. Gap is
It's a fixed
it's fixed parameter for the whole network. Yeah.
And if you're disabling MAC retransmissions, you're basically saying that if packet fails or if a packet fails in the chain of packets that you send, you're just going to retrieve later. How does that work?
So there are no transmissions. If packet fails, the sender does not know that. So we assume there is some end-to-end error control alternatives to address this question. Yeah. All right.
This philosophy is that acknowledgements create additional clutter on the channel. So eliminate acknowledgements and rely on coding or end-to-end.
Okay.
So we have some simulation experiments to evaluate the performance of D-LSMA. Basically, the scheduler we used here actually is per packet reservation, so we don't introduce any flow information parameters in the scheduler. And the reservation gap is fixed at 1.5 milliseconds. And we also changed the default NS2 model to have a fixed one-hop interference model. Basically, the transmission range and the interference range both are limited to 250 meters. And the channel rate is 1 Mbps. All the simulation time is around 200 seconds, and the packet size used for the CPI traffic is over 500 bytes and 1024 bytes. First, we show simulation results for grid topology. Basically, we have a 16 node in a grid topology, and we have 2 vertical flows and 2 horizontal flows at the same time. We try to measure average throughput and delay per flow, and this actually, and then compared this picture showing the aggregated throughput for these total 4 flows. You can see that when the overload increase, the 811 MAC actually saturates at this point, but the D-LSMA actually gets 30% more throughput than the 811 MAC scheme. And also the end-to-end delay is significantly reduced when you have increased the overload. And sometimes the delay will increase dramatically for 811 MAC, but for D-LSMA, the end-to-end delay is always less than 100 milliseconds. We also show some simulation with the random topology, which have 4 flows, and the path is fixed as follows. So in this simulation, we compile the throughput of these 4 flows, A, B, C, and D, which is showing here. The throughput and delay measured when overload is over fixed rate and 110 kbps. And here we can see that the flow C actually has degraded performance due to the heavy contention in D-LSMA MAC, but in the D-LSMA MAC, because it provides relief for this contention by enable parallel transmission and release more capacity in the local neighborhood. So it does not happen in the D-LSMA case. Latency also showing the same pattern. In the final simulation, I want to present, I compiled the D-LSMA MAC with the MAC-P scheme, which was proposed by Rup, and the default 839 MAC in the random topology. So we can see here the D-LSMA MAC actually achieved better throughput than MAC-P scheme and 811. This is because the MAC-P scheme, it tried to align both data and ACK frames, so it introduced more control overhead to compromise performance. And also showing here the fairness among these multiple flows is also good for D-LSMA and better than the MAC-P and the 811 case. In overall, we can say the D-LSMA is a feasible solution to improve performance in a multi-hop environment in 811-based networks, but the throughput increased 20 to 30% due to that capability to schedule parallel transmissions. But this is still lower than our expectation, because by allowing that one-hop interface model to replace default RTI model, we actually should have something like a 200% improvement to allow parallel transmission. Or basically, why this does not happen, we have the following lessons learned from D-LSMA. First, we have some mixed data and control in the same channel, which cause problems like the reservation signaling, like RTI-CTS, actually subject to the cell collision and heavy contention with other RTI-CTS signaling and data traffic. And the exposed terminals somehow cannot be fully eliminated by this effective signaling. Also, this reservation gap selection actually is also difficult. If you have a very small reservation gap, you don't have a chance to allow parallel transmission. But the reservation gap is large, you actually waste some bandwidth for excessive waiting before the transmission. And the other observation is that congestion in path crossing areas also is the bottleneck for the high end-to-end throughput. This can only be addressed if you have some kind of scheme can also solve routing path selection. Optimization of a single layer cannot provide this kind of improvement. Also, we try to say that this kind of one-hop interface model actually may not be really suitable for the dense mesh environment, because the interface model is oversimplified. Okay.
Go ahead. I had a question on the previous slide.
Okay.
So the fixed size of the reservation gap that you're using,
Yeah.
did you always keep it higher than the number of parallel flows that you're going to transmit? In other words, is this the best we'll see with this kind of approach? Suppose you wanted to schedule 4, did you keep the fixed size greater than that so that you could?
Yeah, if you want to schedule 4, you keep it larger than 4. But currently, I put it in 1.5 millisecond test. So yeah.
But in your simulations, you kept it larger so as to see. So these numbers that you're reporting are for it's not limited due to the reservation gap, but due to the fact that due to the bullets 1 and 2, right?
I think this.
I mean, if you consider the third bullet, limitation of a fixed size reservation gap, as a separate thing that you can do some way. Suppose you, for example, you assume that.
You know that this, if
you assume that that's solved, are the first 2 bullets the reason for the?
Here, so basically, this is some kind of go back to the maximum scheduling question. That if you really know that there's 4 link transmissions, you can arrange at the same time. Then you put the reservation gap to allow 4 transmissions, and you are going to get the optimal solutions. But the case we try to derive here is a protocol design which does not rely on the knowledge of the traffic, right? Basically, so this is so we set a fixed parameter which can at least allow 2 parallel transmissions, and to see if it's suitable for the general random topology. And the case, and based on results, we have these following lessons learned. Basically, all these contributed to the performance loss. I think that.
But how much did each contribute?
Okay,
That's fine.
yeah.
That's fine. And the second question I had was in your MS2 simulator.
Yeah.
When you say oversimplified interference model,
Yes.
is that related to, you know about it, right? The SINR model or did you use the physical
No.
interference
I
model
don't
of
say
packet,
the.
or the packet interference model. When you ran the simulation, what model did you use? Did you use the SINR model or the packet model?
The NS2 is based on packet model, right?
Okay,
Basically.
so that's what you use.
Yeah.
Oh,
We don't have calculate the bit error rate per
Right.
bit per bit. So always simplified is not in this
I
sense.
understand. Yeah, that's
My sense is that in the dense machine environment, the simple models actually assume communication range is equal to interference range, like the one hop. So interference range actually can be determined by very simple label discovery, and the interference can be prevented by somehow broadcasting to one hop labels. But the more accurate models for this mesh network actually exist. So basically, like the one proposed by many researchers to use the protocol model of interference, when you have both transmission range and the interference range. And the interference range actually is larger than the transmission range. So for this case, condition for successful transmission is that the node is within the communication range, and any nodes within the interference range is not transmitting at the same time. This example showing that when the interferer K actually is within the interference range of J, but cannot be known by J, the transmission from I to J actually will fail due to this kind of interference. Another kind of model to estimate this transmission range, try to use the carry hop model. So basically K is an integer, so we can say K is 2 hop. So basically the interference range is actually 2 hop. So any node within 2 hop of the receiver shall not transmit. So what's the implication of this kind of interference modeling? Basically we can say, if you really want to establish distributed interference-free scheduling, you have to solve two problems. First, you have to characterize interference whenever the topology change, something like that. So each node in the network have to identify all the conflict links for its incoming and outgoing link. The other, for real-time reservation, you have to establish interference avoidance for every scheduling decision. Each node needs to increase or notify all the interferers for its intended scheduling link access and let them know to obey the scheduling rules. Suppose the topology change is not very dramatic. The calculation actually can be done by some kind of broadcasting scheme in a relatively long time period. But interference avoidance, because you have it done for real time, if you really try to have interference-free scheduling, you need to unicast to every node and get confirmation from that interferer in a very short time period. So we compiled this communication overhead for different models here, showing that for simple one-hop models like RTS, CTS model, you only, for interference calculation, you're in the order of one communication. For interference avoidance, you have to communicate with all the labels of your label. So here M denotes the average number of one-hop labels. But for the K-hop model, this communication actually scales to a very large overhead. Basically, to interference avoidance, you have to have M raised to K notifications sent out to each interferer to let them know you are going to use this slot and they are going to avoid using that. So basically, this kind of analysis helps us to understand that conflict-free link scheduling actually is not a very good approach for per packet mechanism. Because for each packet mechanism, you try to establish interference scheduling, you introduce a lot of overhead. If the K is, say, 3 or 4, it's better to avoid this overhead to do the per flow scheduling. Basically, you can reuse the scheduling results for every packet in the same flow.
But if you do the per flow scheduling, so your traffic pattern need to be.
Yeah, that's why I say that the IRMA approach is for the long-lived flows. The flow has to be.
So if you have a burst traffic.
Yeah, that's why we have both two designs. So basically, per packet scheduling, you have to somehow either you abandon this goal, you don't want to interference completely interfere, like you use RTS, CTS, you just hope for the best. The other way, you have to have some scheme to compact this all kind of notification in a very short time, and to establish this conflict-free scheduling. So this is the dilemma. Actually, this is very difficult for perfect scheme.
And also back to your this D-LSMA protocol, right? So if you reserve multiple transmit period, this is more flow-based.
Yeah, but this is not completely for from the beginning of flow to the end of flow. This is only for multiple packets. So this is so we have this interface to extend D-LSMA to flow-based scheduling, single hop flow rate based on single hop flow rates. But we deem this is not a very complete solution because that control mechanism is not very good. You mix data and control. Basically, if the RTS CTS fails to achieve a conflict-free schedule, all the three transmissions scheduled in one time frame will may be subject to hidden nodes. So that's
for this D-LSMA, does it require the network to be synchronized?
no, because you only
have a reservation period.
the reservation period actually is can be the offset from the label channel events, right? Basically, like 811, you use that NLV vector indicate that one is the beginning of the actual data frame and one is the end of that. Yeah.
Locally.
Yeah.
Locally.
And the RMA design is derived to address this control problem. Basically, we try to establish integrated routing MAC scheduling. And in this work, we actually establish a analytical framework to obtain optimal resource allocation and throughput bounds for end-to-end traffic over single-channel wireless mesh networks. And based on the results of our approach, we derive some system protocols which features separation of control and data, and have some centralized and distributed heuristical algorithm to realize joint routing MAC scheduling. The performance evaluation for RMA protocols are conducted for two main metrics. One is the end-to-end throughput. The other is the control overhead incurred by this kind of global control plane design. Here is an example to show the benefits of the joint routing and scheduling design. In the first figure here, in the 4x4 grid topology, we have two flows which use the 811 MAC with designated mean hole path. And these two flows actually select like the adjacent to each other, so they are going to cause a lot of interference among these two flows. This timeline showing that how 811 MAC work with this kind of topology. The tiny pink block shows the backoff caused by RTS CTS change and the channels carrier sensing. So in overall here we can see after during this time duration there are only two data frames actually transmitted successfully in this in this single channel. However, if we can somehow find a route which is different from this selection, for example, here the second flow uses an alternative route which causes less interference with the first flow, and if we can align the data and transmissions align each other, we can see in this same time duration we can have 8 data frame transmissions. Basically, this shows a 4-fold performance gain can be achieved by carefully selecting routing paths and MAC schedule jointly. But how do you realize that? We think that this can be only used for the flow-based management and over TDMA slower assignments. So the layer 2 and layer 3 protocols are designed based on the flow session rather than packet session. So scheduling results won't change till the end of traffic session. Basically, this can provide better end-to-end performance and less overhead. On the other hand, the traffic flows over the high-speed wireless mesh network, as we have modeled, is not simply conventional internet traffic. because it's a aggregated client traffic, we can say the flow is probably large for a certain time period and require very large backtest transfer throughput. So to better serve long-lived CBR and VBR, the TDMA kind of MAC is better because if the traffic is not bursty, it really requires deterministic bandwidth and delay. And by simply satisfying the inference constraints, one can guarantee a certain fixed data rate at a given link. And as we propose, this wireless mesh architecture is for a small network. Some global synchronization issues can be overcome for a small network. And this is an example showing if we can have a physically separated control and data by putting a control slot in each TDMA frame, so we can avoid the collision between the control signaling and the heavy data traffic. Before describing our protocol, I first want to address the analytical framework to find the capacity bounds for integrated dynamic scheduling. Here is an example showing if we have electrical graph like this, and each edge has some nominal bandwidth limit BE. Suppose there are m concurrent flows from each source to each destination, and suppose the link path is known as the path as links shown in red color here, and each flow has the overload demand as R. This maximized network throughput problem can be formulated as a linear programming problem, like you want to maximize the sum rate of each flow, while the flow is subject where the problem is subject to flow conservation constraint, which the flow have to keep same along the path, and the link capacity for each link involved for all the flows has to be less or equal to the bandwidth capacity, and this has to augmented with the constraints which for link conflict based on the conflict graph given by the inference model. And finally, we can introduce a fairness trade-off parameter Q, which requires that each flow has to achieve at least the Q ratio of the given traffic demand. Based on this model, we conduct some linear programming optimizations for different network topology. We try to solve the analytical throughbound for following with the protocol inference model, which have both communication range and the interference range is larger than the communication range. For the following scenarios, first, suppose we can have optimal link scheduling, but the routing path is already known as the mean hop path. Second scheme we solved is the route is actually uncertain. Basically, the traffic from S to D can split in multiple different routes. This is the multipath routing scheme combined with optimal scheduling. Actually, this is a linear programming problem, but it's not very hard and can be solved. And the single path routing actually is very difficult to solve because it requires that we have each flow, we only have one path from the source to destination, but this path is not known. It can be any path. This turns out to be a mixed integral programming problem. And we use some kind of technical called maximal utilization rounding to get an approximated solution. Here is the detail of this technical. Basically, we try to obtain optimal single path routes to get to know how the capacity bounds for the network with single path routing. This kind of single path routing can be modeled as following two constraints. Basically, for each flow at each link, the capacity has to be less or equal to the bandwidth multiplied by an integral variable z. So z is either binary or 1. And for each node in the network, the sigma of the z for this flow and the E is belong to the old edges originated at this node to sum to 1. So because these two constraints, we ensure that for each outgoing link there's only one is active. But because these integral programming problems is very hard to solve, especially for a network with more than 20 nodes, we solve this problem without any. We first solve the problem without any single pass constraints. Then for each flow, we have some kind of solution, which is actually multipass. Use multiple paths to reach from source to destination. Then we identify a set of undefined paths with each carries a fraction of the traffic. And this picture showing the flow decomposition results, which have the 5 routes here, R1, R2, R3, R4, R5, and each have the certain traffic amount. Then we choose the one with the maximum fraction of traffic routed through it. Here the R4 is chosen because it has 7 unit traffic routed through from source to D. Then we solve the linear programming problem with known path sets as this chosen path to get a system throughput bounds as the approximate solution for optimal single path routing problem. We compile the optimal solutions obtained by linear programming with the practical solution simulation, which use DSDV and 811 protocols. First, we use the path sets selected by DSDV protocol as the mean hop path and couple it with the optimal scheduling. Or the other LP solution is obtained by using single path routing with scheduling. Finally, is the multipath with scheduling. We can see here the throughput is obtained by linear programming optimization with optical scheduling up to 200%, 300%, 400%, then that of 811 system depends on different strategies. This is true for 5 topologies here. We can show here there's a high potential to achieve better end-to-end throughput with some integrated routing and MAC design. Also, we use some simulation. Well, we do some analysis to find that how this aggregated network capacity scale with the network growth and traffic sessions. So basically, you can see here for different network size from 10, 20, 40, 60 node network, the aggregated throughput actually increase very slowly. This actually conforms to the theoretical analysis, basically say the given n node randomly located in a U disk, the aggregated transport capacity actually with interference-free protocols is in the square root of n over log n. So this somehow indicates that per node capacity actually does not scale for this flat architecture. So this so to really have superior performance, we have to limit the network size to a certain degree. Also, it shows that for different number of traffic sessions here, when you have multiple concurrent flows, have more concurrent flows, the network capacity will actually decrease. Here you can see the decrease. Basically, it shows that somehow if you use a large number of concurrent flows in the network, you lose the advantage to have alternative optimal paths to have better end-to-end performance. Based on the analytical framework and some analysis, we propose to have a IRMA protocol design to realize that IRMA protocol design actually have a physically separated global control plane and data plane. So all control signaling is on a separate plane. The parameters of IRMA components in the data plane here is determined by the control algorithm executed by IRMA agent, which is running in the control plane, use separate routing bootstrap protocol and the MAC protocols. the whole system is work like follows. First, the network can bootstrap and do some topology discovery and inference calculation. After that, you can load default IRMA parameters. So the system is the optimization is triggered by traffic variation detection. So if there are any new traffic session occurred, the optimization is triggered and design a new set of paths and schedules and to distribute these results to the whole network, then go back to the working state. For this IRMA framework, we propose both centralized algorithm and distributed algorithm. The centralized algorithm, we assume there is an existing central entity collecting global information like topology and bandwidth and inefficiency relationship and run optimizing algorithm. And this assumption, we propose two algorithms. One is the C-IRMA MH, the other is C-IRMA BR. The C-IRMA H actually solve Multihop routing and optimize link scheduling based on routing results and real-time flow demands. The C-IRMA BR algorithm attempts to optimize routing and scheduling decisions simultaneously using available MAC bandwidth information to route around congested areas. The distributed algorithm have same kind of objective, but it does not have this centralized entity to do that. So each node needs to figure out the best schedule and path for its traffic in a distributed manner with local information exchanging only in the control plane. Actually, the optimization for this is done from source to sink hop by hop. First, I'm going to describe the centralized algorithms. The C-IRMA MH algorithm is a very simple greedy algorithm. Basically, it conducts the TDMA link scheduling based on the path selection in a centralized manner. So the inputs of this algorithm is like topology and traffic profile and the TDMA frame length, which is the system parameters for the whole network. And the output is the route selection and TDMA slot assignments for each link. The algorithm is conducted as follows. For each flow, we find the shortest route, which is the Multihop metric, with Multihop metric in the graph, and get a link set S. And then for each link in this S, we map traffic demands to slot demands, and then loop this link set to assign an earliest available slot X for this link, as long as it does not conflict with the link's already scheduled in this slot. Then, is this done, we decrement the slot demand, and we'll repeat the step 3 until all the slot demands equal to 0 or no more slots available to schedule traffic. The C-IRMA BR algorithm is different because we try to avoid to only use Multihop routes. I try to have some automated route to route around congested areas. To do that, we use following algorithm. We sorting the flow in ascending order for the slot demand requirement. Then for each flow, we generate a link metric based on the available free TDMA slots. Then we find the shortest path with this new metric, with this new bandwidth metric for this flow, and assign conflict-free TDMA slots for this flow, which is the same as the procedure used in C-IRMA MH algorithm. So with this kind of algorithm, centralized algorithm, we can somehow find the routing path and route around congested area, like in this figure. For example, in this 36-node topology, for two flows A to B and C to D, if we use the C-IRMA MH algorithm, we have two parallel path selections. But with the C-IRMA BR algorithm, the second flow can route around this congested area to have superior end-to-end performance, better than this C-IRMA MH results.
So what is your balance metric? I mean, somehow has to have some spatial sort of notion.
You mean the bandwidth metric?
Yeah.
Bandwidth is basically the metric is how many bandwidths, how many free bandwidths. So basically, there's a slot length T, right? If you have some schedule is reserved, then you mark that slot as occupied, and you count how many number of free slots is in the schedule, and use that occupied slots number as the bandwidth metric. So basically, it means that the occupied slot number is small. That means the link is good. Yeah.
So in this scheme, how did you address the fairness issue? So basically, you sort all these flows, right? If your flow 1 require all the bandwidth you have, right, and you don't have bandwidth left for the other flows.
Yeah, basically here is yeah, so that's why we want to sort in the flow in ascending order. So basically, if the traffic demand for the flow is less, we arrange it first. Yeah, basically, if you arrange a flow which have heavy traffic demand and arrange it first, then you use all the bandwidth, and then the following flows cannot be arranged. So there's a fairness issue, yes, here, I admit. Yeah. So for distributed algorithm, actually we use some kind of local signaling to establish distributed TDMA schedule. Here we introduce following signalings like a slot request, slot approve, and slot reject to reserve the slot for schedule one hop link transmission. And we use the schedule update message to coordinate labels interference to mark the slot in free, takes OK, OK, prohibited state here. So this state machine is somehow similar to the one used in the D-LSMA, but here we use a separate schedule update signaling to notify the slot reservation results, and we also introduce schedule cancel signaling to release slot if they are no longer needed for this link. Suppose the flow is ended, we can use this schedule cancel signaling to release it and correct some schedule errors if the collision is detected. Because this is a distributed algorithm, somehow if you conduct the reservation in parallel, there is no guarantee that the link schedule can be 100% free of interference. So, and based on the MH algorithm, we also designed the Dmrbi algorithm, which is a feature to hop joint routing scheduling decisions. And basically, the Dmrbi algorithm is working like follows. We put all the potential forwarders for a hop in a candidate pool, and the candidates are sorted based on the combination of two metrics. The first metric is the distance to destination. The second metric is the available bandwidth for this hop and the next hop. And for example, here, if there's a flow from S to D, the node A actually it has a potential of orders like B, D, and C. But by compare this metric M1 and M2, they determine that the B and D actually is in an interfered area. So you can choose a candidate which with less interference metric, and maybe it's not a mu hop direct in the mu hop, it's not has the shortest distance to destination. But combined with these two, you can choose an interference aware direction like here C. So it can route his traffic to C, and then C can conduct same kind of joint routing scheduling to choose a different route to reach destination. Basically, if the one of the next candidate is failed, we use that schedule cancel signaling to revoke the previous reservations and choose the next candidate in the candidate list. If all the candidate list fail, all the candidates in the list fails, we reserve the fallback to the mean hole path here. So we conduct performance evaluation for IRMA protocols in S2. So we implemented the signalings in the global control plane and the IRMA algorithm, and we compare the performance of the IRMA protocol with two following baseline approach: DSDV plus 811 and the LDV plus 811. The S2 simulation parameters is as follows: the topology size is 1,000 by 1,000 meter, and the transmission range actually depends on how many nodes in the network. It's shrink correspondingly. The data channel rate is 1 Mbps. The control channel rate is 100 kbps. The SNR threshold is 10 dB with the two-way ground model, and the slots per frame is 40. So this is the main results about the showing the performance between the IRMA algorithm and the baseline approach, which use DSDV and 11 or LDV and 11. You can see here the IRMA protocols actually for different number of concurrent flows in the topology always achieve something like 200% gains than the baseline approaches. And here also D-LSMA MAC algorithm actually achieve amount to 90% of the C-LSMA MAC. Both bandwise routing algorithm behave better than the Multihop algorithm in average. Actually, the Mrbi algorithm achieve 22% more throughput than C-LSMA MAC algorithm. And the Mrbi algorithm actually the result is mixed. They only achieved up to 2.37% more than the D-LSMA MAC algorithm. This is because the Mrbi algorithm is not very good here because the per hop selection, because we don't have that kind of rollback mechanism. When you make a decision in that hop, you cannot forfeit it. So, but the selection is based on some information. The local schedule information might be changed. Is volatile because of some of the other flow reservations actually may be revoked by the other node to reserve flows. So this is showing that the distributed bandwise routing joint scheduling is somehow is very difficult to design to have performance as good as the centralized algorithms here.
Actually, for your scenario 3, the distributed is better than centralized.
This one.
Right.
This is the distributed MH algorithm.
MH.
Yeah, this is the centralized MH algorithm. Actually, this can be explained like this. Basically, in the centralized, this is something related to analytic simulations. In the centralized scheme, we use the strictly protocol interference model, which involve the communication range and inference range. But this somehow creates some artifacts and overprotection. With overprotection, that means that if the node is within the interference range, it may not really cause generate interference enough to interrupt your transmission. If your transmission is very near, your transmitter is very near to receiver. But in this kind of effect can be avoided by use distributed algorithm. Distributed algorithm actually have some kind of link level detection about collisions. So basically, it somehow can have this kind of parallel transmission, which is prohibited by the centralized algorithm. So this is due to the discrepancy between the NS2 modeling for centralized algorithm and distributed algorithms here. Yeah.
So your interference modeling is restricted sometimes?
Interference model is restricted.
In the sense it's kind of like it prevents you to communicate sometimes when you should really.
Yeah.
Right.
This is the artifacts I call is overprotection. There are some other artifacts in the interference modeling, but this for protocol design, you really rely on some kind of simplified protocol models. Yeah. And this is an experiment showing the control overhead comparison between our C-LSMA MAC algorithm with the baseline approach. Basically, the overhead statistics here is the baseline approach. We take all the CTI signaling and the control and the routing overhead as the signaling overhead, and compare it with all the control signaling generated in the global control plane. Here, showing here, the simulation is run as in a 4x4 grid, and we have 10 traffic sessions generated with random start and time, with average duration is 30 seconds. The whole duration is 60 seconds, and the traffic start at after time is longer, and after t equal to 20 seconds. And the results are normalized by end-to-end throughput. Now here showing that the C-LSMA MAC algorithm actually has significantly lower overhead compared to the baseline approaches. This is because showing here we can see that there's a lot of control signaling overhead for baseline approaches due to the RTS-CTI exchange for every packet. But this is totally avoided in our C-LSMA MAC algorithm. With C-LSMA algorithm, we only have some certain specs corresponding to the new traffic sessions generated here. So basically, it's on-demand control signaling generation here. So this example shows the URMA approach reduces the signaling overhead because per flow control is much more efficient than the per packet control.
So the overhead mostly generated by RTS, CTS for your...
Yeah, for DSDV you have the periodical routing overhead also. For LDV you have that flooding routing request overhead.
Yeah.
I think it's both.
Yeah.
About how much percent would be routing? Out of the 7% overhead, how much is routing?
I think that the maybe 2% about routing, the 5% is about the RTS TS flow. RTS TS provide a constant flow because you have to do it for every packet.
But
The routing is too critical.
LDV, right? After you set up the route, if you don't do the route refreshment, so it's pretty much that's it, right?
Yeah. So
You
basically,
don't have that much routing overhead.
somehow I think the LDV is behave like here because the LDV used some kind of that flooding scheme. Basically,
You only flood at the beginning.
you flood at the beginning, but
If you have a long
because remember that
long flow,
in this comparison, the data and the control is combined in the same channel for the baseline approach. So basically, the LDV flood may not be perfect some way. So somehow the node might miss a 1 sequence number and think that the router is gone. They might going to do another round of flooding due to the loss of control signaling. Because LDV, the signaling is also carried in the same channel with the data traffic here.
you use the vanilla LDV or the modified LDV.
I use the default LDV in S2. Yeah.
So you don't have route refreshment and all these things, right?
I have to check that. I don't have an answer for this. Yeah. Finally, we want to compare the overhead of the centralized protocols and the distributed protocols. Here you can see we compare the Zhibin Wu algorithm with D-LSMA algorithm and compare the overhead here for different network size and different number of traffic sessions. You can see the routing and the scheduling results need to be disseminated when each traffic session starts and ends for centralized algorithm. This somehow does not scale with the increasing number of the field hosts and the size of network. So when you have more and more number of traffic sessions, the overhead grows very quickly. Also, if the network size grows, the overhead also increase. But for distributed algorithm, the most overhead comes from the system bootstrap discovery and the schedule maintenance and the schedule update messages. So all demand scheduling routing overhead is very trivial. So we can see here the curve is almost flat for different number of traffic sessions. For 5 or 8, 10, 15, and 20 traffic sessions, the overhead is almost flat. Based on the product design practice of URMA and this thesis, we have following conclusions. First, we established an analytical framework to get optimal resource allocation and showing that the super bounds achieved by joint route scheduling for end-to-end traffic flow over single channel wireless network can be much higher than the layered approach. And actually, we also provide some mechanism to solve this network capacity problem, especially for optimal scheduling with single pass routing strategies. We also designed a perfectly linked scheduling protocol. It can alleviate both the hidden terminal and export terminal problems. It helps supporting single or multiple flow real-time flows in various ad hoc networks. Finally, we proposed URMA framework to realize flow-based conflict-free switching. The URMA solves MAC and routing problems together with joint optimization with both conflict-free link access and congestion-aware routing sections. It can be extended to support end-to-end flow quality of service. And the simulation results show that the URMA protocol could provide 200% to 300% improvement in network throughput for long-life CPR flows with modest signaling overhead. Also, based on the design practice of these two protocols, we propose some design strategies for high-speed wireless mesh network. First, to achieve both interference-free access and optimal scheduling lead to superior MAC performance. And interference modeling is important in this picture because various models of interference is remarkably different performance. Appropriate modeling in this mesh environment should go beyond one hop. And the non-trivial overhead actually exists for interference calculation and reservation. To guarantee the conflict-free switching, it's better to separate data and control to ensure the reliable delivery of control signaling. And per-flow switching protocol is better than per-packet mechanism for following reasons. First, you can reuse reservation results for consistent traffic and require less overhead. You can keep improving schedule by packing more overlapping transmissions in a relatively long time period because the flow is not like a packet which disappeared just immediately. And you can optimize the routing and MAC scheduling jointly for extra performance. Some future working directions can be, first we can extend our proposed research methodology for multi-channel, multi-radio wireless mesh networks. By incorporating channel assignment also in the picture, we can conduct joint routing, TDM, and FDM optimization, and get the system capacity bounds, and then realize this kind of joint control with the help of global control plane. We also see here that the CSMA-based approach is good for short-lived flows, bursty traffic like D-LSMA design, but IRMA is good for consistent traffic. So it's better to have dynamic switching mechanism between the CSMA and TDMA. Basically, some ongoing work is done in the orbit test bed with some design with the help of GNU radio. Also, we can apply this integrated design for a more general mesh backbone. Suppose the constraint about the transmission range can be relaxed. We can see if this can be also used in the cellular level framework to have some kind of like which hunted you can at level multihop mesh use the same kind of design philosophy. Some future work can be work on fairness and improve fairness and quality of service mechanisms. So I'm happy to answer further questions about my thesis.